All right, so it's my pleasure to welcome you all to the big exam of Abhishek Sharma, who probably needs no introduction given his extensive involvement with different kinds of activities in the department. Over the years, that includes his participation in the women's group, in the CB podcast, and also for having received the Hui Award last semester. So as you know, after graduating from IIT Delhi in 2016, Abhishek came to Cornell, where he had an interesting beginning, I would say, in that it took him a while to find a home for research. And I guess it's fair to say that it was unclear at the time if our group would be a good match for him. I'm happy to report now that it was, as you will see. And so as you know, in research, problems tend to be harder than you think they are at the beginning when you look at them. But in some cases, you already know that the problems are non-trivial and that it would take a special soul, someone fearless with great attention for detail, the drive to search and digest and learn from lots of papers, and have the creativity to find solutions and even imagine methodologies. So I gave tricky problems to Abhishek, so problems that I already knew were going to be non-trivial. But those problems have clearly met their match, as you will see in his talk. Now, for those in the audience not familiar with the area, don't be fooled by the apparent simplicity of his systems. Yes, we like to strip them down to their bare bones to allow us to describe these fundamental interactions between the particles, and then we gradually flesh them out, adding more detail, because we want to understand why and how some particle shapes, for example, self-assemble into very particular ordered structures, especially when entropy plays a key role. And entropy is usually this fuzzy player that is not so well understood. So I can tell you that Abhishek's systems were sort of devils in disguise, which I guess makes Abhishek a successful exorcist. But so, as you know, after Abhishek's presentation of his research, there will be a period of questions from the general audience. After that, this audience will be asked to leave the meeting so that the committee can try to torture Abhishek one last time. So, okay, that's my introduction, and I guess we are still waiting for...
Don is here.
Oh, Don's here, okay. So, Don, can you hear me?
Yes.
Yeah, so I started without you, just the introduction, but I guess Abhishek is ready to go.
I heard you say how wonderful entropy is.
Yes, yes. That's...
Now we're ready.
It's a controversial statement. Please, Abhishek, go ahead.
Okay, just once again, can you guys see my screen and my laser pointer? Perfect.
Yep.
So let me adjust this thing here. Okay. So thank you, Fernando, for that kind introduction. I certainly consider myself an exorcist of sorts. And thank you for everyone who showed up here. As I said earlier, I went through the participant list, and I'm glad to see so many names from very different parts of my journey that have led me to this point of defending my PhD. I'd like to first of all thank you all for being here. Last many of you heard from me was when I was working on biopharmaceuticals, and so this is going to be very, very different for you all. Today, my goal is to talk about my research as much as possible while trying to communicate all the things I've come to learn over the years. Of course, portions of this talk are going to be aimed at very smart people on my committee who are well acquainted with the subject matter. But for everyone else, if by the end of the seminar, you could take away at least one thing that you did not know before, or you feel excited about what I do, I'll be successful. So the work I do, as Fernando mentioned, deals with the self-assembly of nanoparticles. So let's start with why nanoparticles are interesting. Much like how a single water molecule can lead to emergence of an intricate snowflake, we are interested in how a nanoparticle shape can influence the assembly of a large number of such units in a colloidal solution. This work is also motivated by the recently gained ability to synthesize particles of exquisite shapes with high monodispersity. If you take a colloidal suspension of such particles and compress them by increasing the osmotic pressure, they tend to form interesting ordered assemblies that find very useful applications in plasmonics and photonics. Further, these also form ideal systems for studying how anisotropy at the individual units can influence the emergent structure at a large scale. While these interesting experimental observations have been corroborated, the experimental observations have been corroborated by modeling studies as well. We study these systems through hard particle Monte Carlo simulations, where there is only one rule to the interaction, that the particles should not overlap. This abstraction allows us to study the entropic effects of the particle shape, decoupled from the enthalpic effects arising from the forces between the particles. The overlaps are detected using the separating axis theorem, which was derived by Minkowski nearly a century ago. The simulation sampled the configuration space according to the metropolis criteria, and the simulation boxes have periodic boundary conditions, much like the Pac-Man universe. This allows us to simulate if the box is large enough, this allows us to simulate an infinite bulk phase. Now I'll illustrate how one of these simulations look like and how they can show us the ordering transitions take place. In 1950s, when we first got hold of computers to do simulations, hard spheres was among the very first systems to be studied. At low pressure, you would expect them to be all over the place, like in an ideal gas. But now when I compress it, initially it will get denser and denser, and you could think it is becoming a glass. But right when you think it's going to go nowhere, it snaps into a close packed lattice, which is much more compressed than the liquid. And if particles are on a lattice, we call that order translational order. If I were to plot the pressure versus volume fraction for hard spheres, I would get an equation of state where there are two branches, a liquid branch and a solid branch. At some pressure, the liquid spontaneously transitions to the crystal. We can also calculate a freezing point, much like what a 0 degrees Celsius or 32 degrees Fahrenheit for water to transition is. But unlike that particular transition, which is triggered by a temperature change, these transitions take place through a change in pressure, more specifically osmotic pressure. So such a pressure where the free energy per particle, mu, the chemical potential, is equal in both liquid and solid phases is known as coexistence pressure. And all the liquid above that pressure is known as metastable liquid. That is, the solid phase is more stable than the liquid phase. And the driving force for that transition is given by the difference between these two chemical potentials. Now, what happens when you introduce facets into the particles? Well, let's find out with these cubes. One thing you will be quick to notice is that now our particles have orientational degrees of freedom, and they are colored accordingly. Right now, they're pointing all over the place, but as I compress them, you will notice that they start getting denser and denser, and then eventually they transition to some kind of order. But what is interesting about this particular kind of ordering is that it is not only translationally ordered, but also that there is an orientational order where particles are pointing in the same direction. Such modeling studies have found interesting ordered arrangements spontaneously arising out of compression of systems with faceted particles, from space-filling structures to the ones with well-defined voids. This work has very interesting connections to spatial packing of various shapes, which was one of the main reasons why I decided to work on this project. But these particles may not only form crystals, but they also form phases with intermediate order between complete disorder and complete order, known as mesophases. Whereas in the crystal, there is translational and orientational order. Based on geometric properties, certain shapes can form phases that lose one of the two kinds. Appreciable rotational symmetry can lead to stabilization of rotator phases or plastic phases, where particles are arranged on a lattice but point all over the place. On the other hand, high anisotropy stabilizes liquid crystalline phases where particles all point in the same direction but are not arranged on a lattice. And you can potentially have transitions between any of these phases. And over the last 4 years, I have worked towards understanding how such phase transitions take place through the simulation of a variety of shapes. Simulations also provide a unique opportunity to study such processes since they can reveal finer details at the microscopic level. While at the macroscopic scale, you can observe a visual change in the appearance of supercooled water turning into ice. A simulation can allow for a direct observation of the molecular rearrangement and the emergence of structure in slow motion. Excuse me. In my molecular simulations, the snap transition in hard spheres that I had shown you earlier can be better understood in a similar fashion. If I look closely, if I find that the ordering originates at a single point in an ordered nucleus, which grows from then on. Generally, this process is well described by classical nucleation theory, where a nucleus of a stable phase embedded in the metastable phase has a free energy described by a bulk term and a surface term. The surface term dominates for small nuclei, and the bulk term eventually overcomes, leading to a critical nucleus size beyond which the nucleus is favored to grow, and an associated free energy barrier, which is directly related to the nucleation rate. To study this process in our simulations, we first need the ability to classify whether particles are ordered or not. And for that, we use functions known as order parameters that take in the configurations and give you a score on how ordered each of your particles are. A simple example is that of these ellipsoidal particles. If you consider these two pairs, you would intuitively say that the one on the left is more ordered than the one on the right. One way to translate this intuition mathematically would be to take dot products between the orientation vectors. But how do you go about characterizing complex orders such as cubes, which have more complicated symmetries? We resort to these functions known as spherical harmonics, which for many of you must be familiar from fluid mechanics or quantum mechanics. For various values of n, they can capture a number of symmetries we observe in many lattices. These functions translate a particle orientation to a high dimensional complex vector that can be used in a manner similar to a dot product to tell if two particles are aligned or not. Extending this to bond vectors, you can also capture translational order as well. Once we have an appropriate order parameter in place, we can approach the task of studying nucleation process and calculate the nucleation barrier. In computational studies at small driving forces, the nucleation barrier is large, and therefore nucleation itself is a rare event with a minute probability of occurrence during a simulation run. It is important thus to develop special techniques to study a rare event like nucleation in a computationally efficient manner, because you do not want your simulation to run forever. Hence, we use biased simulation techniques such as umbrella sampling that break down the barrier into more manageable chunks, and then we can stitch the results together to obtain the barrier height. Using such approaches, we have calculated the nucleation barriers for a variety of shapes, which allows us to look into trends on whether certain faceting raises the nucleation barrier or lowers it instead. We learned that the way particles are faceted have important consequences on these barriers. At the same driving force, we find that certain shapes like octahedra are harder to nucleate than spheres, whereas others, like truncated octahedra, are easier to nucleate. These trends can be partially attributed to the level of facet alignment between the particles intrinsic to the growing crystal lattice. In case of truncated octahedra, in the crystal, you find that each particle is aligning its facets to its neighbors. And such motifs are actually favored in the disordered phase due to entropic effects, similar to the depletion forces some of you might be aware of. On the other hand, for octahedra, the prominent configuration in the growing crystal leads to a suboptimal level of facet alignment, and hence Formation of configurations like these hinders the growth of the crystal, and hence there is a higher free energy barrier. This work was featured on the cover of journal Soft Matter in March 2018. Facet alignment is one of the many important factors when it comes to the kinetics of self-assembly. My findings over the last 4 years or so can be broadly classified under 4 different themes, which I would like to talk about today, starting with the mostly published work and slowly sharing with you some of the recent findings that will be published in the near future. Besides facet alignment, another important way to explore the kinetics is to look at the influence of interfacial free energy between ordered and disordered phases. This theme first originated when we investigated cubes. The cubes seem quite straightforward as a shape and probably are the first faceted particle that comes to anyone's mind. However, they do not have a very simple phase behavior. The ordered phase also, although it is translationally and orientationally ordered, has an unusually large number of vacancies, and particles in it can diffuse in and out of lattice positions. This particular feature enables a rapid resolution of grain boundaries, which means that if you have 2 crystal grains placed flush to each other, they will eventually resolve and form an intermediate grain to resolve the conflict. On the other side of the same coin, you can say that the disordered phase is ordered as well. If we look at the probability density of various states along the orientational correlation for neighboring particles in both these configurations, we find that there is a decent overlap between the phase space occupied by the 2 phases. That means there are plenty of ordered motifs present in the disordered phase. Contrast this with another shape like octahedra, where there is a minimal overlap and there is a clear distinction between the 2 phases. This manifests in an unusual abundance of ordered domains in cubes, present even at 0 supersaturation. And in 2018, we reported that during a transition, there is not one nucleus consistently growing unimpeded like a nucleation and growth scenario. Instead, the transition appears to take place through a bulk mechanism. And during this transition, initially uncorrelated domains become increasingly correlated over the course of the ordering. The high incidence of such ordered domains hints at the ease of forming disorder order interfaces. And if I go back to the free energy expression for such a domain, it would translate to a low interfacial free energy between the disorder and ordered phase. Hence, we started looking into ways to directly measure interfacial free energy for cubes using a method known as cleaving walls method. And the implementation of this method is relatively straightforward. You need to start with the equilibrium configuration for the 2 phases in simulation boxes with periodic boundary conditions. Then you use artificial walls to cleave the configurations reversibly to the point where the particles cannot interact across the gap. Then you transpose the configurations leveraging the periodic boundary conditions such that dissimilar phases face each other across the gap. Dissimilar phases face each other across the gap. Finally, you reversibly close the gap, and throughout this process, you measure the pressure experienced by the cleaving walls, and you calculate the work done upon the system much like you would calculate it based on, say, for a gas being compressed by a piston. And this work done upon the system per unit area of the interface created gives you the interfacial free energy between the 2 phases. Here's a summary for the calculation performed to obtain interfacial free energy for cubes. So our hypothesis was that this value should be a low value, but how small is 0.088? Well, to put it in context, we put together the reported data on interfacial free energies at various supersaturations for other hard particles. So we have hard spheres, octahedra, and other polyhedra. And if I compare them to hard cubes, I find that the cubes form a clear outlier with an unusually low interfacial free energy. Every other shape except for cubes undergoes nucleation and growth on this plot. I started by pointing out that large number of such ordered domains could be a consequence of low gamma. And now that we know that that is indeed the case, I would like to substantiate that statement through a model that can relate the two quantities and explain why the cubes have such a large concentration of ordered domains. At the steady state conditions in a metastable disordered phase, particles could either be disordered or ordered in a cluster of size n. Then we can then use the law of mass action to relate the concentration of these species, much like how you would do in a chemical reaction, and then apply a mass balance on the distribution, limiting up to the critical nucleus size to restrict ourselves to the metastable basin. We can now numerically solve for this distribution to obtain the distribution of particles across the different species and obtain the fraction of ordered particles present in the disordered phase. We call this toy model mass action derived classical nucleation theory, or MAD-CNT. Upon solving the model for spherical clusters, we obtain interesting trends, noticeably that the fraction of ordered particles remains relatively low except for this downward diagonal band. I would like to note that the toy model certainly does not apply to such high fractions of ordered particles, given that the clusters would eventually impinge and interact with each other, and that is assumed to be not the case in the model. Nevertheless, it is instructive to compare these results to actual calculations. And while quantitative comparison is difficult, we could qualitatively place most of the systems following well-behaved nucleation and growth near the top of this plot where the ordered domains are rare. Cubes, however, hover relatively close to where we might expect a higher fraction of ordered particles to be present in the disordered phase. This model essentially corroborates the unusual observations we first made in 2018, indicating that the unusually high concentration of ordered domains could indeed be a consequence of low interfacial free energy. An open question that still remains is, why would cubes have such a low interfacial energy to begin with? And we have a couple of hypotheses around this. One has to do with the roughness of the interface, in that the roughness correlates with the cost of interface formation, and cubes presumably have the flattest interface you could think of. It may also be influenced by the complexity of the lattice, which is also quite low for cubes, in that the unit cell is quite small and it's quite, the instructions to grow the crystals are going to be quite minimal. In other work along these lines, we have also predicted an increase in interfacial free energy as we truncate the corners of the cubes, which could also have interesting consequences as to at what point does the nucleation and growth start being the dominant mechanism for the transition for these guys. This work is also going to be featured as a supplementary cover in an upcoming invited issue of the Journal of Physical Chemistry B. And the tools we developed in this particular theme nicely connect to the next theme I want to talk about, where I focus on the effect of particle anisotropy on the kinetics of disorder-to-order transitions. When I first started here, one of the first shapes Fernando provided me was this odd-looking shape known as gyrobifastigium, in short, GBF. It is a Johnson solid made up of squares and equilateral triangles, sort of two roof-like prisms joined together with a twist. Fun fact, fastigium actually means roof in Greek, I believe, or Latin. I'm not sure. This shape is interesting to us because it can fill the entire space on its own. And also it does it on a unique lattice known as ABCD lattice after the periodicity of the stacked layers. To our interest, this shape does not form a mesophase. And also it does not spontaneously transition to the ordered phase in unbiased simulations. You can, however, seed it toward the transition, much like how you can insert a sugar crystal into a supersaturated sugar syrup and have it grow. So if you insert, let's say, a spherical seed, it quickly grows into a prolate geometry. And this was quite unusual observation for us. And this geometry persists for much larger nucleus sizes. Using a method we published in 2018, we could find that the geometry of the nucleus, starting from an arbitrary shape. If you start from a spherical nucleus, the simulation will eventually converge to the natural shape. And essentially give you what it would look like in during the growth of the nucleus. Recently, we were able to understand better why this shape forming through the measurement of interfacial free energy for various crystal planes using the cleaving walls method I had described earlier. And this information can help us predict the shape of the nucleus if we use a geometric construction known as Wolf construction. This is a century-old construction based upon a derived relation between the length of the normal vector to a crystal facet and the interfacial free energy of the said facet, in that they are proportional to each other. And so you can, if you have the surface energy plotted as a function of orientation, you can simply draw the normals and find the inner volume to obtain the nucleus geometry. Using the interfacial free energies we obtained for various crystal facets in the GBF shape nucleus, we completed a Wolf construction, which results in a shape very similar to what I had shown you earlier from my other predictions. Right now, we are exploring what would happen if this shape was elongated or squished. Would this change the nucleus shape, or would this also change the phase behavior and the kinetics? To answer these questions, we are looking into selected aspect ratios and see what happens with them. For reference, this is the standard case, and here is what the equation of state for the standard case with aspect ratio of √3 looks like. Just to reiterate, we do not observe a spontaneous ordering transition in our unbiased simulations for this particular aspect ratio. And the situation remains quite the same when we consider the smaller aspect ratio, in that there is no change of phase behavior, and there is no spontaneous ordering as well. On the flip side, the things do change when we increase the aspect ratio. We find that for prorate GBF, when you take the disordered phase, here the particles colored with the alignment to the horizontal, if you compress it, it slowly transitions to the ordered phase, and you can start seeing ordered domains emerge in various parts of this simulation box. The branch it reaches upon this transition is not exactly matching with the perfect crystal because of the grain boundaries, but this is exciting to us nevertheless, because we learn that you can ease this transition by simply increasing the aspect ratio. It could also indicate that the interfacial free energy is also decreasing with increasing the aspect ratio, but that needs to be verified. So these results tell us that somewhere in between these two aspect ratios, there is a point where the kinetic barrier is low enough for our unbiased simulations to effect the transition. But what happens when we increase it further? Surely we must expect that the transition becomes even easier, right? Here is what happens when you compress the disordered phase for this long GBF. I have again colored the particles based on their horizontal alignment, and you will see a lot of reds, blues, and yellows, but watch what happens when I compress this, and look out for the red particles. As you can see, the red particles have nearly vanished, and most of the particles seem to be aligned in one direction. More notably, they are not on a lattice. So this is therefore is an orientationally ordered, translationally disordered liquid crystalline phase known as nematic phase, and it has its own branch on the equation of state. But what happens when you compress this phase even further? Well, here is what happens. So if I start with a much more compressed version of this phase, you see the particles are a little more aligned, but they're still not on a lattice. But upon compression, you will see that slowly the order emerges, and the particles start falling onto a lattice, further accentuated by these lines where you can clearly see that all the triangle tops are aligning at. This crystal is quite defect-free as well when compared to the earlier ordered phase obtained for a smaller aspect ratio, and has a comparable volume fraction to the perfect crystal. So we could update the previous picture by perhaps drawing another boundary in between these two ratios to demarcate the stabilization of the nematic phase, and also that the crystal that was formed has minimal defects. On this project, the next steps involve the development of order parameters, calculation of nucleation barriers, and determination of nucleus shapes, as I had stated earlier. Of particular interest also would be the LGBF transitions, where they exist on this two-dimensional space of orientational order and translational order. So we just saw a system of these nematic to crystal transitions where you have an orientationally ordered but translationally disordered state going into a crystal, which has both of them. The next theme complements this particular study by looking into transitions where you start from a translationally ordered but orientationally disordered rotator phase and go into a crystal. So in this case, you would not expect the particles to move that much from their positions, but rather just orient. Just as a refresher, this is what a rotator phase looks like in comparison to the other two standard disordered and crystalline phases. You have particles arranged on a lattice like a crystal, but the orientations are not all the same. Moreover, I'd like to stress that the lattice over here need not be the same as that for the crystal, as we will see later as I talk more about the effects of distortion in the lattice. To study the rotator to crystal transition, we focus on a family of truncated cubes. These shapes are obtained by truncating the corners of the cubes in a systematic manner, and their phase behavior is quite complex, with over 15 possible classifications throughout the family. I'm going to focus in a particular region where the shapes form a liquid phase, a plastic rotator phase, and a crystalline phase. I focus on this particular sliver where most translationally ordered phases are related to the body-centered tetragonal lattice, where you have particles occupy the corners of the unit cell and the body center, and one of the dimensions of the unit cell is longer than the other two. On this phase diagram, you could perhaps consider two different scenarios, which I'll illustrate for two specific truncations, 0.572 and 0.527 and 0.572, henceforth referred to as TC52 and TC57. We choose these two particular shapes because, as you can see, for TC57, it goes from a standard BCT lattice to a BCT lattice, whereas the TC52 goes from a standard BCT lattice to one with distortion. This change, this difference sets up a stage for us to study how distortion can play a role in these transitions. If we look into the equations of state for these two particle shapes, there's a general similarity with an isotropic disordered phase, a crystalline phase, and a rotator phase being present for both shapes. Here are some sample snapshots for various phases where you can clearly see the presence or absence of orientational order based on particle colors. Please note that the lattice distortion between these two may not be as evident here, but I'll make it clearer later on. The rotator phases for both shapes are quite similar, and if we plot the orientation vectors, it reveals that there are 18 preferred orientational sectors for these particles in the rotator phase. Given the octahedral symmetry for these particles, this can be brought down to 3 distinct orientations that are distributed throughout the lattice. They are not in particular congruence with the lattice vectors, so based on the literature, we could expect there to be a first order transition between the two phases. With clarity about these rotator phases in place, we can now look at how these phases compare with the crystalline counterparts, especially focusing on the lattice distortion. One useful way to capture that effect is to look at the coordination number as a function of distance from a particle present in this lattice. For TC52, where the lattice changes, we find that expectedly there is a major difference in the coordination shells. While the rotator phase seems to have 12 nearest neighbors present, the crystal has a segregation between the two. It has 8 first nearest neighbors and 6 second nearest ones. If you look at the nearest neighbors around a given particle over here, the differences compound over the distance. Moreover, if you look at the orientational correlations between the neighbors in both these phases, we find that while in crystal, you have neighbors mostly aligned with each other, in the rotator phase, nearly 2/3 of the neighbors are misaligned, which would tell us that the three orientations present in the rotator phase are quite well mixed. On the other hand, for TC57, where the lattice does not change, we find that the coordination shells remain similar, and even the nearest neighbors look quite similar as well. Interestingly, the orientations seem to self-associate a bit more with less than 2/3 of the neighbors being misaligned. Now that I have established the differences among the two lattices, now let's look at what happens when you compress the rotator phases and see if they transition to the orientationally ordered crystalline phases. First, let me focus on the simpler case with the identical lattice. Here again, you see the particles are colored according to their orientations. And as I compress this, you will notice that the particles will permute through various orientations at each of these lattice points. But you will notice that the permutations become a little more restrictive as the transition goes on, and eventually one orientation takes over the entire lattice. To drive home the point that the lattice merely shrinks, here I have plotted the initial and final particle positions on a three-dimensional quiver plot, aligned for clarity to show you how if the system goes from rotator to crystal, there's just compression going on throughout the lattice. Clearly, there is like a sort of an isotropic dilation going on here, and such transformations in the literature are known as dilational transformations. Now, if we compare this with the case with TC52, where we expect the lattice to change significantly as it transitions to crystal, we would find something interesting. Again, when you notice like there are all sorts of orientations present in the rotator phase, and we should expect that one of the orientations would take over the entire lattice. So let's see which color wins in this one. I see a lot of yellow and blue, but let's see which particular color really makes it. It seems like blue is winning, but eventually it turns out that the blue and yellow have a tie between them. And if you look at my virtual background, that's a different plane sliced in the same lattice. This was very unexpected to us because we were expecting all the particles to orient in the same direction, but we find that they are oriented in a layered fashion. And if we look closely at the lattice, we find that the orientations are arranged such that one of the orientations occupies the corners and the other occupies the body centers of the unit cell, much like a cesium chloride crystal. That one, though, has a body BCC lattice. This has a BCT lattice. Hence, we call this configuration an orientational salt. The two orientations result in 12 sectors instead of 18 for the rotator phase. And upon compression of this salt, you do not transition to the crystal. You're very curious as to why this happens. And we think that the key to understand why this does not go to the crystal is to compare the salt with the rotator phase. We find that there is a broad similarity among the coordination shells, and also that you can clearly see that the nearest neighbors also seem to have similar placement. Interestingly, you can also notice that how the green orientations lie on the body centers within a cage of the purple particles. Also, having 4 out of 12 nearest neighbors aligned means that you would by default match the distribution that we had first observed for rotator phases in terms of orientational correlations. Another way to contrast this is to contrast the speculative rotator to crystal transition to the observed rotator to salt transition and look at the lattice displacement quiver plots. For the rotator to crystal transition, there is significant anisotropic distortion that needs to take place, reminiscent of elongational flows from fluid mechanics. Such transformations are known as deviatoric transformations. And on the other hand, if you compare the rotator with the salt, you find that there are very minor rotations or shearing of the lattice that takes place. We hypothesize that this need for drastic distortion is the reason why TC52 does not transition to a crystal and chooses the orientational salt instead. On the other hand, transition for TC57, where distortion is minimal, goes without a hitch. Next on this project, we would like to look into development of order parameters for these transitions, calculate the barriers, and investigate the mechanisms for how these transitions take place. That was the final theme of my work that I intended to talk about today, and I hope these findings contribute to our understanding about how these particles self-assemble, and that the methods and theories I developed here could find use in other systems in future as well. With that, I would like to acknowledge my committee, everyone in the Escobedo group, and Dr. Karthik Nayani from University of Arkansas for helping me with my research, CAC and now defunct ICSE for maintenance of computational nodes, National Science Foundation and Semiconductor Research Corporation for their funding, and all the people in the audience today for paying me the most valuable thing someone can give in these days, their attention. Since I'll only defend this thesis once in my life, I would like to take this opportunity to acknowledge many individuals who were a part of my journey here. I would like to first of all acknowledge several of the faculty members at CBE. First and foremost, I would like to acknowledge Fernando. I could not have imagined a better research arrangement where I could engage in a sincere scholarly discourse. In pre-pandemic times, I could just simply walk into his office and discuss my latest findings within minutes of finding them. Such timely facilitation really accelerated my research, and knowing that my ideas would be received with as much excitement I had about them made me very comfortable and excited to share them in each meeting. I've also been never afraid to share the difficulties I face, and he has really created a stimulating environment where I can openly work on what I don't know and what I am weak about. Also, he enabled a lot of participation in many things outside my research, which I'm really thankful for. I also think that without his advising, I would not be where I am today, both as a researcher and a person. And I think the world would be a better place if we had more advisors like him. Susan Daniel was the director of graduate studies when I was recruited at CBE, and she truly created a welcoming environment for me. And I very much enjoyed talking to her about science, academia, and culture. She's a key mentor, and she actually prompted me to be to increase my participation in CBE-related service, which I'm really, really grateful for. I met Abe Strook on the second day of classes, and he has also been a key mentor in all aspects. He has always been generous with his time, and I've enjoyed conversations with him about research and otherwise, which have led to important ideas that I live by to this day. One of the most important one being that as a PhD student, I need to manage my advisor. He's also one of the best people to ask questions that I know of. And for that reason, he's on my committee. I was also not a great student of fluid mechanics as an undergraduate, but if it was not for Professor Koch's great graduate class and his earnest answers to my questions, I learned it very well. I did very well, and I'm today very confident about my skills in that subject. Had I not already decided on working with Fernando, I would have liked to join his group. Over the years, he was my go-to person for theory advice, which has been very important for many of my projects. I'm thankful for him also for being the special committee member representing applied math, which allowed me to actually take a lot of courses that I really wanted to take in math, for example. I would also like to thank all the faculty members who helped me learn many fascinating things over the years, Professor Archer, Professor Steen, and Professor Clancy, to name a few. I'd also like to thank Professor Brad Anton for giving me the opportunity to relearn so many chemi concepts as a TA for unit operations. Running the distillation column in the continuous mode was one of my highlights of my time at Olin Hall. I'm also thankful to all the current members and all the people I have overlapped with in the Escobedo group. Prajwal Bangalore Prakash was instrumental in onboarding me on the project. He had started in the group 1 semester before I joined the lab, and his familiarity with the project and his collaboration on the 2 course projects that I started my work on really jump-started my research. I enjoy discussing research ideas with him. We often have friendly debates. I think they're friendly. And even outside work, I'm grateful for him for driving me to the ER once when I really needed it. Mayank Mishra over here is my true MVP, really. Even though he spent like maybe little more than a year with the group, he taught me how to do bash scripting, which enabled me to automate my workflow. I was really able to create simulations that analyze themselves and trigger other simulations, which accelerated my research and basically saved me a lot of manual labor so I could focus on more creative pursuits. His attitude is also exemplified in him developing the code which I use to render all these simulations and all the beautiful renderings, which have featured on both the journal covers I have got over the years. Ankita Mukhtar is a competent colleague who I got to share an office with for first 2 years. I enjoyed discussing research problems and exploring the restaurants of Ithaca with her. She, along with Chris Nowak and Yang, were also helpful in explaining the lamps minutiae when I was occasionally foraying into molecular dynamics. Unmuk Gupta and Yang are also acknowledged for sharing their scripts. And everyone else over here is also thanked for their presence. And I have learned so many things in group meetings, listening to them talk. I also owe thanks to many folks who worked on the project before me, many of whom I've never met and I'm deeply indebted to. Bettina John, whose photograph I could not find, wrote the original Monte Carlo code and a lot of related overlap code as well. That is the basis for a lot of my simulations. Umang Agarwal, who did some pioneering work on mesophases that revealed so much science that nearly all my research questions can be traced back to his work in one way or another. I also had a chance to meet Mihir and his help in generating initial configurations for certain tricky phases is appreciated. Vikram Thapar, who is present today in the audience as well, passed me the baton on many of the projects I talked about today. And I was fortunate to be able to collaborate with him on the first paper at Cornell. Many people at CBE enabled a healthy workplace with their presence. Until March 2019, my office was a small cabin inside the Daniel Lab office. I appreciated the entire lab fostering me not very differently from their own members. I also made great friends in many of them. Many in Daniel Lab are very quiet people, and I sincerely apologize if I was ever a disruption to them, given I can enjoy conversation a bit too much at times. Especially Dave and Tiffany have grown to be very close friends to me. Dave in particular, even though we are from different countries, we can still relate as international students and also as scientists. Several organizations at CBE enriched me as an individual, such as JEGSA, DIP, CBE Women, Science Blender. It was through these organizations I gained useful skills and cherished friendships that helped me stay sane. And specifically, a lot of these people helped me never go to a lunch unaccompanied. The staff at CBE was also very helpful and made sure everything proceeded smoothly, whether be it for my academics or my teaching assistantships. And I'm very thankful for that. I have been influenced by many people in my life, and I would like to acknowledge all the science communicators who have exposed me to the wonders of science over the years, be it YouTube or podcasts. I think I belong to the very first generations of people who had access to high quality science content available through online video as I was growing up. I mean, those things look quite banal and look quite rudimentary, but they can actually lead to very serious research. One person I would like to acknowledge in particular is Grant Sanderson from 3 Blue 1 Brown. Many of the people in the audience would know who I'm talking about. While many of his videos inspired me to create some of the techniques I talked about today, I'm more inspired by his knack of creating compelling visuals of mathematical objects. that not only appeal to lay people, but also to graduate students and hopefully to professors. I would also like to acknowledge my philosophy teachers from my undergrad who really taught me how to learn, how to analyze, and most importantly, how to synthesize new knowledge. I think learning philosophy was a major turning point in my life, and I cannot thank them enough for that. I'm also thankful to the great musical artists whose words and art inspired me to keep going through all these years. I'd also like to acknowledge my friends from IIT Delhi, Sahil Loomba and Harsh Parekh are A+ individuals who themselves were on a graduate journey with me in this and remained in constant touch and were always great influences about work and life. I would trust them with anything in my life. Harshad Agrawal also had a similar journey to me. We started in the same undergrad lab, collaborated there, and now here we are both in the United States pursuing our PhDs. We always had things we could relate to each other about. Friends from undergrad, Anshul, Rama, Shravan, Vidisha, Mohit, Yoshita, and everyone else who's in the audience today have been very much supportive over the years, and I'm really grateful for that as well. Last but not the least, I would like to thank my family for their understanding that doing graduate school and science in general brought me happiness. My siblings, especially my brother, has taken care of my parents through all these years, more so recently during the pandemic. It is not easy to let go of your child for such long periods of time like that, especially your youngest one. So their sacrifice is what has enabled all the science I've done today. My brother-in-law is also acknowledged for exposing me to all the encyclopedias and books written by scientists as a teenager that inspired me to be one today. It was only a few decades ago that my parents were based in a rural setting in India, and the fact that their child could be here defending a PhD in the United States, speaking fluent English, is truly magical. Finally, I would like to just say that I wasn't always sure where I would be in my life. I was a misfit, a quiet kid who was always picked on for being weird, for being dorky, for stammering. And I think I'm a product of all my experiences, be they good or bad. And here today, as I'm defending my PhD, it is at least in a certain way that weird kid feels a little more accepted and is a little more confident in his oddities. I'd like to thank you for listening to my talk, and I would be happy to take any questions right now or later through any platform on the screen. Thank you.
Great. Thank you, Abhishek. It was very nice. So they did a really good job presenting your work and also giving it context with your last slides. So I also want to thank you for making so many nice movies. People in my group know that I always ask for them to make movies because I think they are very compelling, not to understand what's going on. So they're there. So thank you. So
yeah, just for context, Fernando had not seen all these movies, many of these movies before. So
really nice. So it's time for questions from the audience. So please, if you want to ask a question, just use your microphone and ask it.
Yeah, Abhishek, can I ask you a question? Vikram here.
Yeah, Vikram, go ahead.
Hey, Vikram.
Yeah, it seems like for the studies in which the orientational order is being nucleated, it seems like it's hard to find a good order parameter to do barrier studies, right?
So we have a few things in work, but go ahead.
Yeah, I was just curious that I'm talking based on my past experience, which was like 5 years ago. That you use I think Q6 for the translation order.
Yes.
I was just curious, have you tried like I4 for this GBF or even
yes.
rotator to the crystal transitions?
Yeah.
So did
so
they
this,
work? Okay.
Yes. So this DI which you see over here is actually DI4. So this is using I4, and you can see that there is some distinguishability. Of course, I mean each particle is going to have some neighbors that are aligned to it. I've actually tried looking into it. there are some phases which are trickier to have order parameters for. But for this one, I'm actually using a combination of things. So I also use this, but I also use the difference in the coordination shell. So I can basically say it has to have more neighbors at that distance.
Okay.
So, but yeah, I certainly agree. It's tricky, and there are some interesting ideas, like especially for the salt. But yeah, that's certainly tricky. One more thing, actually, you'll find this interesting is if I use Q6 for translational order between these two, I actually find that the salt has much higher Q6 than the rotator. So it's more translationally ordered with respect to Q6, certainly. So because I4 would not work here, right?
Because I think generally with the translation order, you have this critical nucleus using Q6. So it's just, very nice talk though. I really enjoyed it.
Thanks for coming. I mean, you're probably one of the best people I could expect here.
Okay.
Hey, Sahil, go ahead.
Congratulations, Abhishek. That was a really good talk. Very crystal clear to somebody who's not even, from the field. So I think I understood most of it. And I think what got me really curious, just asking as somebody who's not in the field, but who studies like social networks or other sort of, complex systems, so to speak, is, what are the next steps here? Like, what are you excited about in terms of, like, it seems like you've played with a lot of interesting shapes, trying to, vary their length, aspect ratios, cut the corners, etc. Like, I'm quite curious as to what's like the next shape you would like to study and why, and sort of what's sort of motivating you to keep working in this field, essentially.
So one of my motivations was that a lot of the transitions that we see over here are kind of analogs to a lot of naturally occurring transitions. For example, solid-solid transitions where lattices change show up in chameleon skins, like to change color. So one of the motivations was that we can actually do a lot of fundamental science over here and ask like what happens when these transitions take place. Also because these are like more, as I mentioned, like you can use these as model systems to study how anisotropy at the unit can affect the emergent order. And so that was one of the motivations. So like you can use the lessons learned here, like the order parameters or the methods I used here to other systems with different contexts. There is not any particular shape I have on mind right now, but I would for certain be interested in what shapes can form these orientational salts in particular, because it seems like quite weird that like such stuff does not really happen as often. I mean, next thing here would be to actually see if you could, so real particles don't just have shapes, they also have forces between them, like van der Waals interactions and charges. So one of the interesting things would be to actually add those enthalpic interactions and see if, you can have interactions that, let's say in octahedra, promote this configuration over the faceted aligned one, and can you configure their phases accordingly. So there are a lot of exciting things. As you know, I'm very much a fundamental guy about my research, so that stuff appealed to me a bit more. Yeah.
Awesome. Congratulations again.
Thanks, Sahil.
Any question from anybody else?
I have a quick question.
Please go
Sure.
ahead.
Yeah, this is just pure curiosity. So in your compression experiments, how do you decide how much pressure is enough?
I just keep increasing it and equilibrate it at that pressure. So, and then eventually, like at some point, it transitions.
Sure, but in some systems it doesn't transition, right?
It does not. Yeah. So okay, yeah, that's a good question actually. So for example, for one of these guys over here, let me open up. So let's say for this guy, I can actually calculate, so in my Monte Carlo simulations, how what's the step for rotations and translations. And that can basically tell me if the system has become glassy. And once it has become glassy, nothing is going to happen. So when I say that they don't spontaneously transition, it's like within like a few million MC cycles. So you could say like the barrier has to be like below a certain kBt for it to transition. It's possible that, but like once it reaches a glassy state, it's not going to transition. So that's when I know it's enough.
Yeah. Okay, that makes a lot of sense. Thank you.
Yeah.
Hi, Abhishek. I have a question. This isn't scientific, since it seems all those got asked, but more just a general question.
Yeah.
After you leave Ithaca, what do you think you'll miss most about Cornell?
Actually, who is asking this? I'm not able to tell.
Sorry, this is Andrew.
Oh, Andrew. Yeah, I guess. I think I have actually missed for last 1 year hanging out with people, but I think I'm going to miss being able to do this research as well. I'll miss the outdoors. I mean, I'm going to a big city after this, and I don't know if I could get the same experience of. I think during the pandemic, it was clear to me that I needed places which are like sparsely populated, and Ithaca is the best place to do that. I could just show up to the Sunset Park near my place and just walk there, and I would be the only one. I'd have the entire park to myself. So I think that's what I'll miss a lot about Ithaca, and definitely the people. I mean, as I grow older, I realize it's more difficult to make friends, and I'm really going to miss the friends I made here.
So just in case, Abhishek, if you want to continue working on this, you can always do it in your weekends, you know?
Yeah, of course. Yeah, but Fernando, work-life balance is very important.
I know. Okay, so it seems like there is no other question. Going once, going twice. All right, so to the general